Hello, so we will start practicing creating visualizations with the seabourn package. In this exercise, we're going to start by loading the Gapminder dataset. Now, just a note, seabourn comes pre-installed with Anaconda. If for some reason you don't have access to seabourn, you can uncomment those two lines and run this code. And this is going to fetch and install the seabourn package. You can also upgrade the package with a modifier -- upgrade. I have seabourn installed, so there is no need for me to run this code. Instead, I'm going to run import pandas and also import seabourn, and I'm going to give both of them an alias. PD for pandas and SNS for seabourn. Now let's load the Gapminder dataset. This dataset you can find under data in the same folder which you've kind of obtained from unpacking the zip file. So if you look at data here, we're basically interested in the Gapminder dataset here. So what I'm going to do, I'm going to use the function readCSV from pandas, and then I'm going to tell it to go ahead and load the Gapminder file. I just press tab to invoke code completion to look up the files instead of typing the whole file name myself. Now this is a TSV file, which means it's a tab separated value file. Which means the values in this file are separated by a tab rather than by a comma. You can actually open this file and you can see that the columns are separated by the tab character. So by default, CSV is going to expect a CSV, a comma separated value file. And in this case, we don't have commas, so we got this error. So what we need to do, we need to tell pandas that the delimiter, which is basically the character separating the two different values, is going to be, in this case, the tab character, which is represented by \T. Once this is done, I'm just going to take a look at the data by calling the method head, which shows the first 5 rows. In this data set, we've got data about country demographics over time. So we've got countries and continents over years, and we have life expectancy, population, and GDP per capita. Alright, so let's start with the first question. Let's relate the per capita GDP to life expectancy. We're going to use a relation plot. So I'm going to use the function relatePlot, which by default creates a scatter plot, and I'm going to map my x to GDP per capita. The question here is not very specific on which one is the x and which one is the y, so I'm going to put my x to be GDP per capita and my y to be life expectancy. So y equal life expectancy. And let's not forget to pass in data. Data in this case is the name of the data frame, which happens to be data. So don't confuse this one, that's the parameter name, and that's the variable name in the notebook. They happen to be the same here. So we've got a scatter plot. So a scatter plot shows some interesting relationship. There is a lot of noise in here, but we can see that overall more GDP per capita translates to higher life expectancy, although you've got some outliers and a lot of variance, especially in low GDP per capita. So let's try to add kind of a nuance here, and let's try to use color to differentiate between different years. I'm going to take the same here command to create the plot, and I'm going to pass hue to be equal to year. This basically will map here to the hue channel, the color channel, and will create lighter dots for earlier years and darker dots for later years. So we notice in here that overall, with more time, further years, we have higher life expectancy, but we still have some variance here. We also find that those outliers here are, relatively speaking, earlier points in time. Countries with very high GDP per capita, but not so high life expectancy around the 1960s and 1970s. Alright, so now let's try to map another variable into the data. Let's try to map the size to population. So I'm going actually to take the same command here, and then I'm going to pass size, in this case equals to population. This will create dots of variant sizes based on the population. Now if you take a look at population, you can see that this is population in million of people here. Now what's interesting in this visualization is twofold. First, that the population label reflects a transformed value of population. And second of all is that the dot size, the marker size, although it's proportional to population, there is not a lot of variance. So what I'm going to do, I'm going to tell it to make it more contrasty by using the parameter sizes. So we've seen the parameter sizes before, and here I'm going to tell it to range the sizes from a certain value, let's say for example 15, to another value, so let's say 300. And that's going to make those dots a bit more contrasty here, from smaller one to larger ones. Alright, so now let's break this plot per time over year, but let's use faceting instead of using color here. And the thing in here with color is that the data is a lot kind of cluttered. So let's try to break things over time, and I'm going to, instead of using hue to equals year, using column equal to year. So that's basically is going to create a plot for each year, and those will be columns here, as you can see. So that shows the relationship in between life expectancy and GDP per capita earlier in time in 1952. And you can see that we've got great variance in life expectancy. But we also don't have, we have some variance in GDP per capita, but it's kind of overshadowed by one outlier here, and most of the countries are below 20,000 US dollars. If you fast forward over time, you can see that we're getting some more spread across the GDP per capita. That reflects, you know, countries getting out of poverty, and we also see, if you look at life expectancy, that countries are pushing further in terms of increased life expectancy. So over time, many countries became richer and became healthier. Although we still have the variance, we have now this wedge shape where you've got a lot of countries with very low GDP per capita, and then you've got this another part of the wedge where you've got more or less a linear relationship between GDP per capita and life expectancy. Now we can do more than that. So we can actually look at continents. So actually here we can look at this distribution per continent. So I can map column to continent here, and that's going to give us a contrast in between the continent. And you can see here that we've got different set of relationships depending on the continent. So if you look at Asia, there is a lot of widespread here in between countries, and don't forget that this is over time. In Europe, it's more kind of more uniform, although you get that variance, more or less the relationship here is linear. And if we add color here, if we add hue to be equal to year, we should expect the lower dot here to be earlier years, right? Especially in Europe in the 50s and 60s, but things got improved in the 70s, 80s, and fast forward. In Africa, you can see that although we've got a lot of variance in terms of life expectancy, GDP per capita is kind of on the low side. In the Americas, we have those two different shapes, a wedge shape, and that probably reflects the kind of discrepancy between North America and South America. In Oceania, it's more kind of homogeneous, right? Because we've got only one or two countries, and you know, more or less you've got this linear relationship. Both Australia and New Zealand improve GDP per capita and life expectancy over time. So this serves to illustrate the versatility of the relationship plot, rail plot, where we can do things with this kind of basic basic plot. And let's not forget that relationship plot also offers us the way to create a line plot. So here, for example, if I do x is going to be year instead of hue, and y is life expectancy, and let's do life, let's actually leave it as is. Let's look at column per continent. That's going to give us the life expectancy over time in those continents. And obviously you've got variance because you've got countries. So if I turn kind to be equal to line, I can get a line with a confidence interval around it, as we've seen. And that basically kind of a more summarizing of the data. It shows you kind of the trend, and it shows you the variance in that trend. And we can see that over time, all across all of the countries improved in terms of life expectancy. Although over time there is still discrepancy across the continent. For example, Africa in 2000, it's still worse than, or almost as bad as the Americas in the 1950 in terms of life expectancy, unfortunately. So, and that's kind of basically just using variation on the relation plot command. Now we can do more plots. So we've actually done this here. How does life expectancy vary per continent? We can do distribution plots, for example. That's one possibility. So we can create a histogram. And this is something we looked at in the introduction session. So I'm going just to switch this from a relation plot to distribution plot. And in this case, I don't really want the x, the x, because I'm looking at the variance of life expectancy. And I was going to create a faceted I forget data here, and kind of the midst of copying and pasting. Let's take a look at the documentation of distribution plot. So distribution plot takes one variable, which is x. So x is probably data at life expectancy. And that's going to give us the distribution plot of life expectancy, right? And we can vary this per continent. So we can have a couple of these, and each one can be shown for one of the continents. Actually, if you put 3 of them here based on continent, they're going to be overlaid. Or we can use this plot. So this plot is a command that works on one variable. We can actually use this plot, which is similar to relation plot. X is equal to life expectancy, data equals to data here. Right, and here we can add more variance, so we can say hue is equal to continent. And that's going to give us this variance here, and we can switch the type to be a step histogram. This basically will take out the boundaries in between the bars for a clearer histogram that shows the over kind of laid portions. So we can do element equals to step, and that's going to give us this step histogram. We can also do a KDE and switch this to a KDE, kernel density estimation, for a smoother version of the histogram. I mistyped the syntax, and probably the issue is that element doesn't exist with KDE. So let's take out element here, and that's going to give us the kernel density estimation of distribution across the different continents here. We've actually partially answered the question, how did life expectancy changed over time? So we can do a relation plot and we can do a line plot. So we can do something like a relation plot. Since this one is only asking about life expectancy over time, we can do relation plot where y y is x is going to be year or time, right? So, and y is going to be life expectancy. And this is going to give us a scatter plot. And let's not forget to pass in data here. That's going to give us a scatter plot. And I want to smooth it with a line plot. So I'm going to add kind equals to line. That's going to give us the trend. And I'm actually going to do different trends per continent. So in this case, I'm going to show color. Well, actually, let's do hue equals to country, because this is actually going to give us a line for each country, and expect this figure to be really kind of busy because you've got all of these lines together. You know, that serves to show that most of these countries, except for some countries plagued by disasters, natural disasters or wars, we have that transition for a better life expectancy over time. And I can break this one per continent, and that's going to give us columns per continent, or maybe I can do it per rows since it's already a bit busy. So I'm going to do different rows. Each row is going to be representing a continent. So we've got Asia here, we've got Europe here, which is kind of more homogeneous. We got Africa, we got the Americas, and we get Oceania as the end. If the interest is only to look at general trends, so maybe it suffices just to have one figure centering across continents, so we can see here the different trends across all of these continents.